Welcome to Ask and Learn.
Okay, well, in this problem, we have an ideal Otto cycle, and we have to answer what is the thermal efficiency. So we actually want the thermal efficiency of the cycle, and what is the rate of heat input. So we actually want Q dot in. So this is the input, the rate of heat input is actually the power. So we can understand this rate of heat as the power that enters this cycle. So how are we going to answer this? First of all, let's remember what is the thermal efficiency. So the thermal efficiency in an Otto cycle is described by 1 minus R K minus 1 divided by k. Sorry, let's rewrite this. This is not good. So this is 1 divided by r, which is the compression ratio, to the power of k minus 1. And k is the specific heat of this gas. So we know the problem says to us that the compression ratio is just 10.5. Therefore, we have 1 minus 1 divided by 10.5 to the power of 1.4 minus 1. Therefore, the thermal efficiency of this Otto cycle is just 0.609, or to simplify, just 61%. So this is the first answer. We just need to remember the equation for the thermal efficiency in an Otto cycle. Now we have to answer what is the heat input. So the heat input, the rate of heat input, Q dot in, is just the rate of work, the net work, sorry, divided by the thermal efficiency. So this is the second equation. We must remember to solve this problem. Therefore, let's see. Uh, the rate of work in this cycle, the problem saying that is 90 kilowatts. And the thermal efficiency we just calculated is just 61%. Therefore, the second answer, which is the rate of heat, is just 148 kilowatts of power that enters the cycle. So this is the second answer and the final answer to this problem. Thanks for watching.